keeping up with all the breakthroughs, all the latest research, it's kind of like drinking from a fire hose.
Totally.
And that's where we come in. Consider this your shortcut, your curated dive into the coolest, most mind-bending stuff happening in advanced physics right now. No jargon, no filler, just the good stuff.
Exactly. We cut to the chase. Today, it's April 2025, and we're going deep on the state of advanced physics, like right now.
And by advanced physics, we're not talking high school physics, right?
Oh.
We're going way beyond, like, what are the actual fundamental bits of reality, the forces? How do they all work together to build this crazy universe we see? It's about the edge of what we know, those big, juicy questions that keep physicists up at night.
Yeah, the really exciting stuff.
For this deep dive, we've gone broad, looking at all the key areas, all the research, the papers, you name it, and we're pulling out the most crucial insights.
Synthesizing it all like a good cup of, yeah.
Yeah, exactly. Your mission, if you choose to accept it, and we hope you do, is to walk away with the most essential knowledge, the surprising stuff, the stuff that makes you go, whoa, I didn't know that. Okay, let's jump in. First stop, particle physics, the world of the very, very small.
Right, so particle physics, it's all about figuring out those tiniest building blocks of matter and the forces that make them dance. And the foundation for all of that, the big theory, is the Standard Model.
The Standard Model, yeah, everyone's heard of it. But remind me, what is it exactly? Like, what's in it?
Think of it as like the periodic table of the universe. It lays out all those fundamental particles that make up everything, quarks, leptons, the gang's all here.
Yeah.
And it also describes 3 of the 4 fundamental forces. Electromagnetism, light, and all that, with the weak force, which does stuff like radioactive decay, and the strong force, which is the glue that holds those quarks together inside protons and neutrons.
Photons, neutrons, right, the stuff inside atoms.
Yeah.
So the Standard Model basically tells us what everything is made of and how those pieces interact through those forces.
Exactly. And those forces, they work through what we call messenger particles, gauge bosons. It's like they're throwing a ball back and forth. And that's how they exert a force on each other. So you've got photons for electromagnetism, W and Z bosons for the weak force, and gluons for the strong force.
Okay, so it's like a cosmic game of catch. And then there's this celebrity particle, the Higgs boson. What's its role in all of this?
The Higgs. Its discovery back in 2012 at CERN was huge, like validated the Standard Model in a big way. The Higgs, it explains how particles get their mass. Imagine this invisible field that permeates the entire universe, the Higgs field. And as particles move through it, the more they interact with it, the more mass they have. It's like they're wading through molasses, and the stickier the molasses, the heavier they feel.
Makes sense. So more interaction with the Higgs field, more mass. But you said there's more to it.
Yeah, so the Higgs interacts differently with different particles, which determines their mass. And that hierarchy of masses, well, that's still a puzzle. We're still trying to figure out why some particles are heavier than others.
So we found the particle that gives things mass, but we don't know the specifics of how it doles out that mass. Classic physics, right? Always more questions. So besides this Higgs puzzle, what are some other big things happening in particle physics right now? Like, what are researchers looking at, both within the Standard Model and maybe even beyond it?
Right, so there's a lot going on. For one, we're still studying the Higgs itself at the LHC, really getting into the nitty-gritty of its properties, like its mass, spin, how it interacts with other particles. We're talking really precise measurements here, looking for even the tiniest deviations from what the Standard Model predicts. Any tiny difference could mean there's something new out there, some new physics we haven't discovered yet.
So even the stuff we thought we had figured out, we're still scrutinizing it.
Absolutely. And then you've got neutrinos. They're like the ghosts of the particle world. Super light, barely interact with anything.
Neutrino, like, I know they exist, but they're kind of mysterious.
Exactly. We know they have mass now, which was actually a surprise. The original Standard Model didn't account for that. But we still don't know their exact masses, the order of those masses, or even if a neutrino is its own antiparticle. It's like, are they matter, antimatter, both? We're still figuring that out.
Matter, antimatter, both.
No.
That's a head-scratcher. How do we even study something that barely interacts with anything?
Well, we build giant experiments like DUNE in the US and Hyper-Kamiokande in Japan. They're designed to catch those rare moments when neutrinos do interact and to measure their properties super precisely. And then there's this thing called neutrino oscillations, where they can basically change their flavor, electron, muon, or tau as they travel.
So like shape-shifting.
Kinda, yeah. And that's already telling us that there's something beyond the Standard Model going on.
Okay, so the Higgs and these shape-shifting neutrinos are keeping physicists busy. You mentioned something earlier, the hierarchy problem. What's that all about?
Right, the hierarchy problem. It's a big one. Basically, there's this huge energy gap between the Higgs boson's mass and the Planck scale, which is this insanely high energy level where we think gravity starts acting all quantum-y. It's like a trillion times larger than the Higgs mass. And we don't know why the Higgs mass is so low compared to that. It's like, what's keeping it down there?
So it's like the universe has this dial for the Higgs mass, and it's set super low, and we don't know why it's not cranked all the way up.
Yeah, basically. And that's why people are looking at beyond the standard model theories, or BSM. They're trying to fill in those gaps, explain those weird discrepancies.
So what are some of those BSM theories? Like, what are people thinking?
Well, there's supersymmetry, or SUSY, which is a big one. It says that for every particle in the standard model, there's a heavier partner particle. It's like a mirror universe of particles we haven't found yet.
A mirror universe. So double the particles, double the fun.
If we can find them, yeah. But so far, no look at the LHC.
So CUSY is still a maybe. What else is there?
There are extra dimensions, which is a pretty wild idea. Some theories say that there might be more spatial dimensions than the three we experience. And if those extra dimensions are real, they could explain why gravity is so much weaker than the other forces.
Extra dimensions, that's some serious sci-fi stuff. Anything else?
Oh yeah, there's plenty more. People are looking for new gauge bosons, new fermions, heavier versions of the ones we know, maybe entirely new types. And then there's flavor physics, which is all about those subtle differences between the three generations of quarks, and CP violation, which is about why there's more matter than antimatter in the universe.
Okay, so it's like not all quarks are created equal, and something messed with the balance of matter and antimatter a long time ago.
Yeah, that's the gist. And experiments like LHCb at CERN and Belle II in Japan are all over that, looking for clues to new physics in those tiny differences. And then there's dark matter, the big elephant in the room. It makes up most of the matter in the universe, but we can't see it or directly interact with it except through gravity.
Dark matter, the invisible universe. But it's got to be made of something, right?
Right, but the standard model doesn't offer any good candidates, so people are looking for weakly interacting massive particles or WIMPs, axions, sterile neutrinos, all sorts of exotic stuff. They're running experiments, looking for dark matter interacting with regular matter, looking for its decay products in space, even trying to create it at the LHC.
So a lot of hope pinned on the LHC. What's new coming out of there these days?
Oh, tons of stuff. For one, they're making incredibly precise measurements of known particles and processes. Like, they measured the B0 meson's lifetime really precisely, and that's a big test of the standard model's predictions about quark flavor. And they're searching for rare stuff, like they saw the production of 3 massive vector bosons at once for the first time. That's a really complex event to detect.
3 massive what now?
Yeah, it's complicated, but it tells us more about how those weak force particles interact. And they even did the first search for tri-Higgs production at the LHC.
Tri-Higgs, like 3 Higgs bosons at once.
Yep. Super rare, but important for understanding how the Higgs field interacts with itself.
Okay, so it's not just finding new stuff. It's also about really understanding the stuff we already know.
Exactly. They're also on the hunt for long-lived particles, which some theories predict, but they're tricky to find because they don't decay right away. And they're running all sorts of clever searches for specific BSM models, trying to cover all their bases. And then you've got the heavy ion collisions, where they smash lead ions together.
Lead ions, like heavy metal physics.
Haha, kinda. But seriously, they recently saw top quark pair production in lead collisions for the first time, which is big. And they released a ton of data from the highest energy heavy ion collisions ever, so scientists all over the world can study the Quark-Gluon Plasma.
The Quark-Gluon Plasma. Remind me what that is.
It's like the primordial soup of matter that existed in the very early universe right after the Big Bang.
Right. So we're basically recreating the Big Bang in miniature at the LHC.
In a way, yeah. And all of this is getting a boost from artificial intelligence now. They're using AI and machine learning to do things like improve the identification of those jets of particles coming from bottom quarks, which is super important for studying the Higgs and top quark.
So AI is helping us make sense of all that data coming out of the LHC. That's amazing. Okay, from the smallest scales, let's zoom out to the biggest, cosmology and astrophysics. What's the big picture there?
So at the cosmic level, our best model is the Lambda-CDM model. Lambda stands for the cosmological constant, which is basically our best guess for what dark energy is.
Dark energy, the mysterious force that's making the universe expand faster and faster.
Yeah, that's the one. And CDM stands for cold dark matter, the invisible stuff that makes up most of the matter in the universe. This model is based on the Big Bang and cosmic inflation, this period of crazy fast expansion right at the beginning of the universe. And it explains a lot of what we see, the cosmic microwave background radiation, how galaxies are distributed, the whole shebang.
Okay, so it's our cosmic roadmap, but I'm sure there are still unanswered questions. What are those?
Oh, tons. Like, what is dark energy, really? Is it constant, or does it change over time? We've got upcoming surveys like the Vera Rubin Observatory's LSST and the Euclid Space Telescope that are going to map the universe in insane detail, and that'll help us understand dark energy much better. And then there's dark matter. We still don't know what particle it's made of. Astrophysical observations tell us it's there, but we haven't actually detected its particles directly.
So we see its effects, but we don't know what it is. Frustrating.
Totally. There's this alternative idea called modified Newtonian dynamics, or MOND, which says maybe gravity works differently at large scales. But so far, dark matter models explain the observations better.
Okay, so dark matter is still the leading contender. What about cosmic inflation? Is that still a hot topic?
Oh yeah, it's still a big deal. It explains a lot about the early universe, but we're still looking for direct proof. We're looking for primordial gravitational waves, basically ripples in space-time from that inflationary period. And they should have left a specific pattern in the polarization of the cosmic microwave background radiation called B-mode polarization. It's like the light has a certain orientation, and these gravitational waves would have twisted it in a specific way. Experiments like the Simons Observatory and the upcoming CMBS-4 are trying to find this signal.
So it's like looking for these tiny, faint whispers from the very beginning of time.
Exactly. And then there's this thing called the Hubble tension, which is causing a bit of a stir.
Yeah, I've heard about that. It's like we can't agree on how fast the universe is expanding.
Right. We have two main ways of measuring the expansion rate, the Hubble constant. One is by looking at nearby objects, like supernovae. The other is by looking at the very early universe, the cosmic microwave background. And the two measurements don't quite match up. It's a statistically significant difference, and it's bugging a lot of people.
So either one of our measurements is wrong, or there's something fundamental we're missing about the universe.
That's the million-dollar question. It could mean our standard cosmological model is wrong, or there's some new physics we need to add. And then, of course, you've got gravitational waves. Since LIGO, Virgo, and Cagra started detecting them, it's been a whole new ballgame for astronomy.
It's like we've opened up a new sense for observing the universe.
Totally. We can see black holes merging, neutron stars colliding. It's testing Einstein's theory of gravity in extreme conditions, telling us about the life cycles of stars, even giving us another way to measure the Hubble constant. And future detectors like LISA and the Einstein telescope are going to be even more sensitive, allowing us to see even further back in time.
Gravitational waves, black holes, all this stuff is just so cool. What are some of the big questions about black holes right now?
Oh, we've got plenty. Like, what happens right at the event horizon, the point of no return? What happens to the information of stuff that falls in? That's the black hole information paradox, and it's a big theoretical challenge. And we're still trying to figure out how those supermassive black holes, the ones millions or billions of times the mass of the sun, formed in the early universe. The Event Horizon Telescope, the one that gave us the first image of a black hole's shadow, is still giving us data, helping us understand these crazy objects better.
And what about galaxies? How do they form and evolve?
That's another huge area of research. We're trying to figure out how the first stars and galaxies lit up, how they change over time, how they merge and interact. The James Webb Space Telescope has been amazing for this. It's seeing further back in time than ever before, and it's showing us these surprisingly massive galaxies existing much earlier than we expected. It's created a bit of a puzzle.
A puzzle? Like what's...
These early galaxies are too big and too mature for our current models of galaxy formation. One idea to explain it is early dark energy, a hypothetical form of dark energy that was active in the early universe. It could have sped up the growth of structure, allowing these galaxies to form faster, and intriguingly, it could also help solve the Hubble tension, so maybe one solution for two big problems.
So early dark energy is a hot topic these days. What about the dark energy we see today? Is that really constant?
Well, the DAI project recently released some results from their big survey, the largest 3D map of the universe ever. They're looking at these things called baryon acoustic oscillations, which are basically ripples in the density of matter in the universe. And their data by itself supports the idea of a cosmological constant, a constant dark energy. But when you combine it with data from other sources, like the cosmic microwave background and supernovae, there are some hints, maybe a 4 sigma significance, that dark energy might not be perfectly constant. It could be evolving or weakening over time.
4 sigma. That's pretty significant, right?
It is. It's not quite the 5 sigma gold standard for a discovery, but it's definitely something to keep an eye on. It could mean that dark energy is more complex than we thought.
Okay, so the universe might be throwing us another curveball. From the cosmos, let's dive into the quantum realm. What's happening in quantum physics these days?
Quantum physics is booming right now, both in terms of fundamental questions and new technologies. Let's start with quantum foundations. Quantum mechanics works amazingly well, but we still debate what it means, what it tells us about reality, like what's actually happening when we make a measurement. How does a quantum system collapse from multiple possibilities to a single outcome? That's the measurement problem. And then there's decoherence, the process where quantum systems lose their quantumness and start acting more classically. It's all about that blurry line between the quantum and the classical world.
So we can build quantum computers, but we're still trying to figure out what it all means.
Pretty much. And then you've got quantum information science, or QIS. It's about using quantum weirdness to do cool stuff with information.
Right, like quantum computing. Everyone's talking about that.
Quantum computers use qubits, which can be in a superposition of 0 and 1 at the same time, unlike regular bits, and that lets them do certain calculations exponentially faster.
Exponential speed up. That's the dream. But I know there are challenges.
Oh yeah, big ones. Building quantum computers is hard. Scaling them up to more qubits is tough. Keeping those qubits stable and free from errors, that's a huge challenge. There are different ways to build qubits, like superconducting circuits, trapped ions, photons, neutral atoms, even topological systems.
So it's like a quantum race, with different teams using different approaches.
Kinda. And the focus has shifted recently. It's not just about more qubits anymore. It's about quality over quantity. It's about making better qubits and figuring out error correction. People are working on logical qubits, which are like groups of physical qubits that work together to protect the quantum information from errors. And we're seeing good progress there.
So it's like, instead of a bunch of shaky qubits, we want a smaller number of really reliable ones.
That's the idea. And the potential applications are huge. New drugs and materials, better optimization algorithms, faster AI, even breaking encryption.
Breaking encryption, that's a bit scary.
Yeah, that's why people are working on quantum-resistant cryptography, too.
Makes sense. So quantum computing is just one part of QIS. What else is there?
There's quantum communication, which uses quantum effects to secure communications, like quantum key distribution or QKD, which is theoretically unbreakable encryption. And then there's quantum sensing, which uses quantum systems to make super precise measurements better than anything classical physics allows. It's good for things like medical imaging, navigation, even fundamental physics research.
So quantum is about more than just computers. You also mentioned condensed matter physics, the study of materials. What's cool in that world?
Condensed matter is awesome. It's about those macroscopic quantum effects you get when you have tons of atoms and electrons interacting in solids and liquids. One really hot area is topological materials. They have these special electronic properties that are protected by topology, which is a branch of math. That protection makes them robust. They can conduct electricity without resistance, or they have exotic quasi-particles like Majorana fermions, which could be useful for building better quantum computers.
Topology, Majorana fermions. This is getting deep. What else are condensed matter physicists looking at?
There are strongly correlated systems where the electrons interact so strongly that it creates weird effects. You get things like high-temperature superconductivity, where materials lose all resistance at relatively high temperatures, or Mott insulators, which should conduct electricity but don't. And we're still trying to understand how high-temperature superconductivity works. It's a big mystery. And then there's non-equilibrium quantum dynamics, which is about how quantum systems behave when you push them out of equilibrium, like with lasers. You can create new, weird states of matter that way. And a big theme in condensed matter is emergent phenomena. It's about how complex behaviors can arise from simple rules when you have lots of quantum particles interacting. It's like how ants can build a complex colony just by following simple rules.
So lots of emergent craziness in the quantum world. What kind of tools do physicists use to study all this?
Oh, they've got the whole arsenal. Lasers, super cold fridges, fancy microscopes, big particle accelerators, quantum computers, and tons of math and computer simulations.
Sounds intense. Okay, From the tiniest particles to the vastest galaxies, now let's talk about the big challenge,
Yeah.
connecting it all. What makes it so hard to unify gravity with quantum mechanics?
It's like trying to fit square pegs in round holes. General relativity, our theory of gravity, and quantum mechanics, which describes everything else, are just fundamentally different. They use different math, different principles, and we need a theory of quantum gravity to understand those crazy places where both are important, like black hole singularities and the Big Bang.
So our two best theories of the universe just don't get along.
Not yet. But people are working on it. String theory is a big one. It says that everything is made of tiny vibrating strings in extra dimensions, and it naturally includes gravity.
Extra dimensions again.
String theory loves them. But there are challenges. We haven't seen any evidence for strings yet. And there are tons of possible versions of the theory. One cool idea from string theory is the ADS-CFT correspondence, which says that a theory of gravity in a certain kind of spacetime is equivalent to a quantum field theory in one less dimension. It's like saying that a 3D volume of space can be described by information on a 2D surface, like a hologram.
A holographic universe. That's
Yeah.
blowing my mind. What else is out there?
There's loop quantum gravity, or LQG. It takes a different approach. It says that spacetime itself is quantized. It's not smooth and continuous, but made of tiny loops. It's like a fabric woven from loops of space and time.
So string theory adds extra dimensions, and LQG makes spacetime junky.
Basically, yeah. There are other ideas too, like asymptotic safety, causal set theory, and emergent gravity, which says maybe gravity isn't fundamental, but emerges from something else.
So lots of ideas, but no clear winner yet. How do we even make progress in this kind of theoretical minefield?
One way is through phenomenology. We look for observable consequences of these theories, even tiny ones, like specific patterns in the cosmic microwave background, or weird signals in gravitational waves. We also look for violations of fundamental principles, like Lorentz invariance, at super high energies. It's like looking for cracks in the foundation of physics.
Cracks that might point to a deeper theory. Well, okay, before we wrap up, what are some of those cross-cutting themes you mentioned, the things that are important across all of advanced physics?
Right, so there's computational physics. We need computers for everything. Simulating galaxies, particle collisions, materials, analyzing data. It's all about the algorithms, the simulations, the big data crunching.
It's like physics is now as much about coding as it is about equations.
Pretty much. And then there's advanced math. It's the language of physics. We need differential geometry, topology, algebra, all that good stuff. And then there's precision measurement. We're always pushing the limits of how accurately we can measure things, whether it's time, mass, or something else. That's how we test our theories and find new physics.
So it's not just about big ideas, it's about really precise experiments too.
Exactly. And finally, there's interdisciplinarity. The lines between different fields of physics are blurring. Particle physics and cosmology are talking to each other. Condensed matter is inspiring new ideas in particle physics and vice versa. It's all connected.
It's like physics is becoming this giant interconnected web of knowledge.
It is. And AI and machine learning are playing a bigger role too, helping us analyze data and even develop new theories.
So big data and AI are shaping the future of physics. So as we come to the end of this deep dive, what are the key takeaways?
It's an exciting time for physics. There's so much we're learning, so many mysteries we're trying to solve. Dark matter, dark energy, the Big Bang, quantum gravity, new materials, quantum technologies. It's all on the table.
And it's all driven by this deep human curiosity about the universe and by these incredibly creative people who are pushing the boundaries of knowledge.
That's what it's all about. We have these great models like the Standard Model and Lambda-CDM, but we know they're not the final answer. We're actively looking for what's next, what's beyond.
And we have new tools, new experiments, new telescopes coming online all the time.
Exactly. 2025 is the International Year of Quantum Science and Technology, and we're seeing amazing progress in quantum computing. The future is bright, and who knows what incredible discoveries await us.
That's the beauty of it, right? The universe is full of surprises. So, to you, our listener, think about it. What do you think the next decade will bring? What fundamental shift in our understanding of the universe is just around the corner? It's a great time to be curious about the universe, and we hope you'll continue exploring